Cool. So the plan for today is to continue talking about energy-based models, which is going to provide a lot of the foundation also to discuss score-based models and diffusion models. Just as a recap, this is our usual slide, kind of providing an overview of all the different things we've been discussing in this course so far. Energy-based models provide you yet another way of defining a very broad set of probability distributions, and so kind of like expanding that green set, which potentially would allow you to get closer to the true data distribution. The nice thing about energy-based models is that they are defined in terms of this energy function f theta, which can basically be anything. So you can pick whatever neural network architecture you want, and by using the expression that you see there, you get a valid probabilistic model where essentially you can get the likelihood of a data point by looking at the unnormalized probability, which is what you get in the numerator of that expression, and then dividing by the total kind of like unnormalized probability that exists. And so, which is just the sum of the numerator over all possible things that can happen. So kind of like probabilities are defined relatively to this partition function, normalization constant, which depends on the parameters of the model. That's kind of like the crucial thing. And the problem is that typically evaluating z theta is intractable because we are interested in modeling random variables, so multiple random variables or random vectors x with many different components, which means that there is a huge number of possible x's that you would have to consider in order to compute the normalization constant, which means that evaluating the probabilities of data points is generally going to be intractable. You can always evaluate the numerator very easily, but it's very hard to evaluate the denominator in that expression. And the good thing is that comparing the probabilities of two data points is actually easy, and this is important for sampling. So if you want to know, you have an x and an x prime, which could be two images, for example. You cannot easily evaluate how likely is any of the two according to the model, but it's easy to figure out which one is more likely, because the ratios of two probabilities, when you take the ratio, basically the two normalization constants, they cancel. And so it's easy to evaluate that expression in terms of whatever energy function, whatever neural network you use to represent f theta. And the price you pay is that, once again, evaluating likelihoods is expensive. And so if you wanted to train the model by maximum likelihood, you would need to somehow be able to evaluate for every data point this expression or the log of this expression, which would be something like this. And the problem is that you have two terms that depend on theta. And so whenever you want to figure out how to adjust theta or how to pick theta to maximize the probability of a training data point, you need to figure out how to adjust the parameters of your neural network to increase kind of like the numerator, the unnormalized probability of this training data point, which is always easy. But then you have to worry about how does changing theta affect the normalization constant. So by how much are you changing the probabilities of everything else that could have happened? And so you kind of need to figure out how to change theta so that this increases, while the partition function, the log normalization constant, ideally also goes down, so that the relative importance, the relative weight of this training data point goes up as much as possible. And again, doing this is hard because we don't know how to evaluate the normalization constant exactly. So it's kind of like different from a likelihood-based model, like an autoregressive model, where this partition function z theta is guaranteed to be 1, regardless of how you choose the parameters of your conditionals, for example, in which case you don't have to worry about, if you were to change some parameters in your neural network, how does the partition function change, because it's constructed by design to be 1, regardless of how you choose your parameters. So you basically only have the first term when you train an autoregressive model, and it's easy to optimize, and you don't have the issues that we have here. What we've seen is that it's relatively straightforward to come up with a sample-based kind of way of describing kind of like an approximation of the log partition function. And in particular, we've seen that there is this contrastive divergence kind of algorithm that will give us a way of evaluating gradients of the log likelihoods, which is what you would need if you wanted to do, update your parameters to maximize the probability of a data point. You would need to evaluate the gradient of this expression here that we're maximizing. And it turns out that it's not too hard actually to figure out how the gradient of the log partition function, how the log partition function changes as a function of theta, or what's the gradient of the log partition function if you have access to samples from the model. And so if you can somehow sample from the model, which we know unfortunately is also relatively hard, but if you have access to samples from the model, then you can figure out, you can get an estimate for the gradient of what you care about by basically looking at the gradient of the energy on the training data versus the gradient of the energy on these samples that you generate from your model. So this has a fairly intuitive kind of explanation. What we're saying is we're trying to figure out in which direction we should now update data to increase the probability of the training data, or kind of like decreasing the probability of some alternative kind of fake synthetic data that is produced by our model. And by doing that, you're kind of like adjusting, you're actually figuring out how the log partition function changes as a function of theta. That's the right expression. And so to the extent that you can generate samples from your model, then you have this contrastive divergence, and it's contrastive because you're comparing, you're contrasting the real data and you're contrasting it to samples from the model. And so you just need to figure out how to adjust your parameters to basically, by following that expression that contrasts real data to fake samples from the model. So the gradient of log z theta would be the figuring out if you were to change the parameters by a little bit, how does the partition function change? So how does the total unnormalized probability that you have change? So if you remember the analogy of the cake that we're dividing up into slices, this term is basically saying what is the size of the slice that we assign to a particular data point. The other term is telling you how much does the size of the whole cake change. And because everything is relative to the size, you have to figure out how to push up the probability of a data point. It is not the size of the slice that matters, it's the relative size of the slice versus the total cake, the total amount of unnormalized probability. And this is the gradient of the log partition function, which we can approximate with samples, basically. The log partition function, yeah, would be the log of the size of the whole cake, basically. Cool. So that was kind of like the recap. And so training energy-based models by maximum likelihood is feasible to the extent that you can generate samples. And we've seen one recipe for generating samples from an energy-based model, which is this idea of setting up a Markov chain. So using this technique called Markov chain Monte Carlo, where essentially the way to generate a sample is to initialize the procedure by sampling x0 from some distribution. Turns out it doesn't matter what that is. But if you think about you're trying to sample a distribution over images, you start with some image. Doesn't matter what that image is at time 0. And then you basically try to make changes to this image, to this candidate sample that you have, to essentially try to make it more likely. Like if you sample from this distribution pi, which you initialize your algorithm with, this could be really bad. It could be just, set values to the variables uniformly at random. So you kind of start with pure noise, and then you kind of need to figure out how to change the pixel values to go towards high probability regions. And there is a principal way to do it, which basically involves trying to try to change your data point a little bit. If it's continuous, you might want to add noise. If it's discrete, maybe you change the value of a single pixel, something like that. Turns out it doesn't, you can basically do many different things and they all work. And that way you propose a new sample x prime. And then sometimes making this little change by adding noise is good in the sense that you go towards higher probability regions, and sometimes it's not. And so what the algorithm does is it checks basically how good this proposed sample is compared to where you are right now. And remember, this is good because in an energy-based model, although we cannot evaluate likelihoods, we can always compare two data points. And so we can always check whether this sample x prime that we generate by making some local small change to the current best guess is better or worse than what we have. And if it's better, meaning that the unnormalized probability of x prime is larger than the normalized probability that we have before we did the perturbation, then we accept the transition and we say, okay, we're making progress. The state at times t plus 1 is this new sample x prime that we generated. And if not, then with some probability, which depends on basically how bad this proposed sample x prime is, we accept the transition anyways.
So, the reason we're sort of adding noise is because we want a new sample which is much more likely in our model. But can't we sort of guarantee that if we take the derivative of the model with respect to x and then add that, wouldn't that instead of being noisy, wouldn't that be progress?
Yeah, so that's going to come up in the next slide, where we're going to use the gradient of the energy of the f theta as a way to perturb the sample, basically. In general, this machinery works regardless of how you do it. The reason, meaning that in theory at least, under some mild conditions on how you add noise, if you were to repeat this procedure for a sufficiently large number of steps, what you get converges to a sample from the true energy-based model. So you can kind of picture this in your head as some kind of local search or some kind of stochastic hill climbing procedure where you're kind of trying to move around this space of possible samples, looking for high probability regions. And the way you do it is you always accept uphill moves and with some small probability, and occasionally you accept downhill moves when the height of the hill would be the likelihood or the log likelihood or the unnormalized log probability assigned by the model. And the reason this works is because this operator satisfies something called detail balance, meaning that if we denote x prime to be the probability of transitioning from one state to another state x prime, we have the following condition, that the probability of being at x under the true distribution we're trying to sample from and transition into x prime is the same as the probability of being in x prime and doing the reverse move going back to x. You can kind of see that this is true because either x or x prime is going to have higher probability. Let's say x prime has higher probability than x. Then the transition from x to x prime is, this t is 1, and the probability of going from x prime to x is exactly the ratio of p theta x over p theta x prime, which is the probability with which we accept a downhill move. And it turns out that if that condition is true, then basically p theta is basically a fixed point of this kind of operator that we're using to propose new states. Meaning that if at some point xt is distributed according to p theta, then xt plus 1 is also distributed according to p theta. And what you can show is that under some condition, you actually converge to this fixed point. So p theta is a fixed point of this sort of operator, and you get there regardless of where you start from. So regardless of how you choose this pi, how you initialize your sample, eventually xt is going to be distributed as p theta, which is what you want, because it's a fixed point of this operator. And I'm not doing justice to this topic. You could probably do a whole course on MCMC methods, but for our purposes, the important thing to note is that there are ways of sampling from energy-based models, namely MCMC. In principle, they work. In practice, what happens is that you typically need a very large number of steps before you get something good. So you can kind of like imagine if you were to start, let's say X is an image, you start with random pixel values, and then you change them one at a time. It's going to take a lot of changes before you get to something that has the right structure, even though you have guidance provided by this F data. So you kind of like know when you're making mistakes and when you don't. It's still going to take a lot of steps before you get something that is good. And so that's sort of like the problem of energy-based models, is that even if you have an energy-based model trained and somebody gives you the right F data, generating samples is expensive. So that's sort of like the price you pay. You have a very flexible model, but sampling from it is expensive. And note that if you wanted to train a model by contrastive divergence, you have to generate samples over and over during training. So it's not just something you have to do during inference time, but even during training, if you wanted to use contrastive divergence, you would have to somehow use this procedure. So very, very expensive, very, 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 very difficult. A slightly better version, which was kind of like just proposed of this procedure, is something called Langevin dynamics, which is essentially a special case of what we've seen before. And it basically works the same in the sense that you start by initializing this process somehow, let's say a random image, and then you still do your steps. You still an iterative procedure where you're trying to locally change your sample into something better. But the way you do it is by kind of like trying to go in the direction, in a direction that should increase the probability of your sample. So what you do is the way you produce this perturbed version of XT is by doing a step of noisy gradient ascent, where you modify XT in the direction of the gradient of the log likelihood. Here, I'm assuming that X is continuous. This only works on continuous state spaces. And so the gradient of the log likelihood evaluated at XT tells you in which direction you should perturb your sample if you wanted to increase the likelihood most rapidly. And then you basically follow the gradient, but you add a little bit of noise. And the reason is that, just like before, we don't want to be greedy. We don't want to always optimize the likelihood. We want to also explore. So we want to occasionally take moves that decrease the probability of our sample, just because we want to be able to move around and explore the space of possible images. But essentially, it is really take your sample, follow the gradient, and add a little bit of Gaussian noise at every step, pre-scaled in some way. And you always accept the transition, at least in this version of the algorithm. There is also a version of this where you accept and reject, kind of like the previous algorithm I described, but it turns out you don't even have to accept or reject. You can always move to xt+1, regardless of whether you land in a state that has higher or lower probability than where you start from. And you can prove that under some technical conditions, again, this procedure converges to a sample from the distribution defined by the energy-based model in the limit of a large number of iterations. Yeah.
Epsilon on both the actual gradient and the noise. Should it be?
Yeah, so the reason we're using epsilon is that kind of like controls the step size. So it's kind of like the step size in gradient ascent or descent. And it turns out that for things to work, you have to balance the amount of noise that you add has to be scaled with respect to how much you scale the gradient. So the signal to noise kind of has to scale in that way for things to.
Discriminative 2 is.
Yeah, so it has to basically, you need to keep the ratio between the noise, the amount of noise, the signal to noise, kind of gradient to noise ratio has to be scaled that way to be able to guarantee this kind of condition.
very small.
In theory, yes. So it's only guaranteed to work in the limit of basically a step size going to 0. In practice, you would use a small step size and kind of hope that it works.
Is the step size going to 0 due to the noise? Like if we move the noise, then you said we have a higher.
So it is because the step size, because we are not doing accept and reject here. So if you remember this version here, we have sometimes we stay where we are, and sometimes we accept or reject based on that. If you wanted, you could use you can just basically here. I didn't really say how I produced this perturbed version. I just said add noise, but in practice, it turns out you can do it any way you want, and it still gives you a valid algorithm basically. And so if you define a way you add noise to it by saying I follow the gradient and I add a little bit of Gaussian noise, that defines a valid procedure of proposing new data points. And as long as you balance it, then you would have a valid procedure regardless, even when epsilon is large. I mean, you would still have the problem that, basically, you might accept, you need to then you have accept and reject. So sometimes you get stuck where you are, so you don't want to take, if you take too much of if the gradient, the step size is too large, you might be, the Taylor expansion is no longer accurate, and so the probability might actually go down, and so then you might get stuck where you are. So it's still non-trivial, but you can, I guess, this is called the unadjusted version. There is the adjusted version, which is basically you accept and reject, and that one can work with finite step sizes. Cool. Oh, question.
Is this faster than just regular mnemonic, or like why would we use this over the previous?
Yeah. So great question, and in general, this is it still in theory can require a larger number of steps, and the convergence is only guaranteed to be in the limit. But in practice, you can imagine that it's a much better proposal because you're kind of following you have a lot more information. Like before, we were blindly making changes to the image. Well, now we're saying, okay, if you have access to the gradient information, you can be much more informed in the way you make proposed moves, and in practice, this is much better in terms of like the number of steps that you need to converge. And and the good thing is that even though the log likelihood depends on the partition function, or maybe I don't have it here, but if you work out the expression, you'll see that the z theta depends on the partition function depends on theta, but does not depend on x. So all x's have the same partition function. So when you take the gradient with respect to x, you just get the gradient of the energy of the neural network. And so computing the gradient of the log likelihood is actually easy, even when you have an energy-based model. And so this kind of sampling procedure is very suitable for EBMs. And it's still problematic in theory, at least. The more dimensions you have, the slower things tend to be. This kind of thing is reasonable to do at the inference time. But even if you maybe need, let's say, 1,000 steps or maybe 10,000 steps or something like that of this procedure to generate a sample, it might be something tolerable at inference time. If you're generating, let's say, 1 million pixels, it's fine to do 1,000 steps of this procedure, or that might require you to evaluate a big neural network, let's say 1,000 times. Might not be too bad. But if you have to do it during training, then things become very, very expensive. So training energy-based models by sampling in an inner loop where you're doing gradient ascent on the log likelihood is actually very, very expensive. And even though this is a reasonable way of sampling from an energy-based model, it's just not fast enough if you want to plug this in as in this kind of contrastive divergence subroutine, where for every training data point, you have to generate a sample from the model. If to generate this sample, you have to run a Langevin chain with 1,000 steps, things will become just too expensive, basically. So what we're going to see today are other ways of training energy-based models that do not basically require sampling. Yeah.
Slide back.
Yeah.
I don't see how 0.2 is true. Like why is that equivalence true?
Which one?
So the gradient of the log p theta equal to the gradient.
Yeah, sure. So let's see. When we have it here, this expression here is the gradient of the log likelihood, right? Just the log likelihood. F theta minus log z, which is just the log of this expression. Now, if you take the gradient with respect to x of this thing, log z theta does not depend on x, and so it's 0, and so it drops out. And so that's why, basically, yeah, this is true. Great, and so yeah, the plan is to essentially introduce ways of training energy-based models that do not require sampling during training, at least. And so think of them as alternatives to contrastive divergence, which was an approximation to the kind of KL divergence between data and model. So an approximation to maximum likelihood training. That's how we introduced contrastive divergence. What we'll see is the usual trick. There's going to be some other kind of divergence, some other way of comparing model to data that does not involve where the loss function basically does not involve the partition function. And now, if we train by that instead of by training by approximating the KL divergence, then we get much faster kind of training procedures. And so we'll see a few of them. We'll see score matching, which is kind of like the key building block also behind diffusion models, noise contrastive estimation, and adversarial training. So recall that we have an energy-based model, which is defined like that. And if you take the log of that expression, we get this sort of the difference between the energy, which is whatever the neural network you're using to model the distribution, and then you have the log partition function. And the key thing is that the score function, or the gradient of the log likelihood with respect to x, so note this is not the gradient of the log likelihood with respect to theta, which are the parameters of the model. This is the gradient with respect to x. So this is basically how does the probability change if I were to make small changes to the sample itself, not how the likelihood would change if I were to make changes to the parameters of the neural network. So this is gradient with respect to x, not with respect to theta. This is also a function of x, in the sense that at every axis there's going to be different gradients, and a function of theta because the log likelihood itself is parameterized by a neural network with weights theta. And just kind of like what we just saw before, the gradient of the log likelihood does not depend on the partition function. So kind of here, I guess it's shown a little bit better than what I was trying to show before, but if you have the log likelihood is the difference of these two terms, the log partition function is the same for every x. It depends on theta, but it does not depend on x. And so when you take the gradient with respect to x, the log partition function doesn't change. And so the gradient is 0. And so that's why we were able to use the score function or the gradient of the log likelihood in the previous sampling procedure. It's easy to compute if you have access to the energy function f theta. And you can see it here, this kind of idea in play. If you have a Gaussian distribution, where as usual the parameters would be the mean and the standard deviation, remember the partition function is kind of like this normalization constant that you have in front that guarantees that the integral of this function is actually 1. If you take the log, you're going to get the log of the normalization constant, and then you get the log of this exponential. And then when you take the derivative with respect to x, you get again a function of x and the parameters of the model, which is relatively simple. It's kind of like just like x minus the mean scaled by the variance. And if you have a gamma distribution, again, has a potentially nasty normalization constant in front. And if you take, but the moment you take the score, that normalization constant disappears. And you get a much simpler function to kind of work with. And so kind of the intuition is that S theta, which is the score, provides you an alternative view of the original function, where you are looking at things from the perspective of the gradient instead of looking at things from the perspective of the likelihood itself. So if you imagine you have a p theta, which is just a mixture of two Gaussians, let's say in 2D. So there is a Gaussian here and a Gaussian up here. So it's a mixture of two. So you have this kind of fairly complicated level curves. You know, the likelihood is just a scalar function for every x. It gives you a scalar, which is kind of like the height of this curve, where you can imagine you have two bell curves, one centered here and one here. The score is basically the gradient at every point. It's a function that at every x gives you the gradient of the log likelihood. And so it's a vector field. You can imagine that at every point there is an arrow, and the arrow tells you what is the direction that you should follow if you wanted to increase the log likelihood most rapidly. And so as expected, you can see that these arrows are kind of like pointing towards the means of the Gaussian, which is kind of like what you see here, in the sense that if you are at a data point and you want to increase the likelihood, you should push it towards the mean if the model is a Gaussian.
Fixing theta, right? Like the model parameters are fixed.
Well, they're not necessarily fixed, so we're still going to learn them. But when we take gradients with respect to x. And so theta does not depend on x. And so when you take the gradient with respect to x, that the log partition function disappears. But we're still going to be learning theta. So here, of course, I'm just showing a snapshot where theta is fixed. And theta would represent the means and the variances of these two Gaussians. And if you change those, the score function itself would change. And you can kind of see it here. It's still a function of theta, but it's a simple function of theta that does not depend on the normalization constant. So you can compute it without knowing the relative you don't need to know relative. Remember that the gradient is telling you how the likelihood changes if you were to make small changes to x, and we know how to compare the probabilities of two data points in an energy-based models. So it kind of makes sense that it does not depend on the partition function. Yeah.
Yeah, in this case, the score function is basically a vector field representing the gradients. In general, is it always like a vector field, or what is it supposed to represent in general?
It's always, yeah, good question. So the score function, as defined, is always a vector field in a sense representing the gradients, because by definition, it's just the gradient of f theta with respect to x. And so in general, f theta could be much more complicated than a mixture of two Gaussians. And so you can imagine that these arrows would be much more complicated, and they might, if you have probability mass spread out in a complicated way, the gradient could be, it's still going to be a vector field. It might not have that simple structure where it's just pointing you towards these 2 points, but it's still always going to be a vector field of gradients.
Or it can be like a vector field of some other quantity.
So it's a vector field of gradients if it's defined like this, because it's actually a conservative vector field because there is an actual underlying energy function. When we talk about score-based models, we'll see that we'll just use an arbitrary neural network to model this. But for now, we're assuming that there is an underlying f theta, an energy function, and this is just the vector field. So if you like analogies with physics, you can kind of think of f theta as being kind of like an electric potential, and s theta as being like the gradient of that, which is like a field, basically, an electric field. And they kind of like describe the same object, but in slightly different ways. And so there is no loss of information. We're just thinking of things in a slightly different, taking a slightly different view. That is going to be beneficial from a computational reason because we don't have to worry about the partition function. Okay, so how do we do, the key observation is this score function, the gradient of the log likelihood with respect to the inputs is independent of the partition function. And so the idea is that we're going to define a training objective where we're going to compare two probability distributions or two probability densities, P and Q, by comparing their respective vector field of gradients. So the idea is that if P and Q are similar, then they should also have similar vector field of gradients. If P and Q are similar, at different x's would have similar gradients. So one reasonable way of comparing how similar P and Q are is to say, what is the average L2 difference between the score of P and the score of Q? So at every point, we look at what is the direction that you should follow if you wanted to increase the likelihood of P most rapidly, what is the direction that you should follow if you wanted to increase the likelihood of Q most rapidly, and we check how different they are. So it's a vector, so to turn it into a scalar, we take the norm of this vector, and then we're averaging with respect to P in this case. And what I claim is that you can imagine that this is a reasonable kind of like loss function, because if P is actually equal to Q, then the gradients are going to be the same. So gradient of log P is going to be the same as gradient of log Q. This vector is going to be 0 everywhere, and this the norm is going to be 0, the average is going to be 0, and so what's called the Fisher divergence between P and Q is also going to be 0. So it's kind of like a reasonable way of checking how P and Q are different from each other. And crucially, the reason we're doing it is that at the end of the day, we're interested in training an energy-based model. So let's say P is going to be the data, Q is going to be the model. But crucially, this loss function only involves the scores. It only involves this gradient, which we do not depend on the partition function. And so this might give us a loss function that is actually very suitable for energy-based models because it does not require you to know the log partition function of the model. That's kind of like why we're looking at this. So it's a different loss function. It's a different way of comparing probability density functions. They're actually related to each other. So in a certain sense, the Fisher divergence is kind of like the derivative of the KL divergence in a certain way. So if you take two densities and you convolve them with Gaussian noise, and you take the derivative of that with respect to the size of the noise, it turns out that that's the Fisher divergence. But just think of it as a different kind of divergence.
P data, the ground truth, why do we need a model?
Yeah. So let's see how, it's not going to be as easy, but that's sort of like the idea is that let's define a loss in terms of the score because we know how to compute the score and we don't know how to compute the log likelihood. Now, so that's sort of like the score matching idea. P is going to be P data. Q is going to be the energy-based model, which is parameterized by this energy function. And then if you evaluate that Fisher divergence between the data density and the model density, you get this kind of thing, or equivalently, this sort of thing, where you take an expectation with respect to the data distribution of the difference between the gradient of the true data generating process and what's given by the model.
Also assuming that P data is continuous.
Yes, this only works for continuous densities, yes. And so that's basically we're comparing the gradients of the true data distribution with the gradients of the model, which are things we can compute. And even though P theta is an energy-based model, this loss function only depends on the score, which we know we can compute efficiently without having to worry about the normalization constant. So that's the idea. Now, as was pointed out, it feels like it's not very useful because it still sort of like involves the gradient of the log data density, which we don't know, right? It seems like a reasonable loss function, but not exactly one we can evaluate or optimize because although we have access to samples from P data, so presumably you can approximate this expectation with respect to P data with samples, it looks like we need to know the gradient of the log data density, which is unknown. If we knew what log P data is for every x, then we wouldn't have to build a generative model, right?
Why did you know that? I mean, if you take the derivative with respect to theta, like wouldn't the first term be zero?
It's a square. We'll see that there is a square there that creates a coupling, unfortunately. But it turns out that it's almost easy to do.
Just that.
Yeah, not as easy as that, but it turns out that, yeah, so that's sort of like the expression. And the problem is that we only have samples from p data, and so it looks like that first term, the gradient, the score of the data distribution is unknown. So we don't know how to optimize that objective function and try to make it as small as possible as a function of theta, because we cannot compute this first term here. We only have access to samples from p data. That's the usual setting in a generative modeling problem. But it turns out that you can rewrite this loss function into an equivalent one that no longer depends on the unknown score function of the data distribution by using integration by parts. And so just to see how this works, let's start with the univariate case. So x is just a one-dimensional scalar random variable. So the gradients are actually just derivatives. And so just because integration by parts is a little bit easier to see that way, so I'm still using the gradient notation, but these are actually derivatives. And then we don't have to worry about the norm of the vector because, again, the derivatives are just scalars. And so the square norm is just like the difference of these two scalars squared. So that's what the loss function looks like when x is just a single scalar random variable. This basically is the same exact expression, except that it's no longer a vector. It's just the difference of two scalars, and that's what's happening there. And then we can expand this or by just explicitly writing this out as an expectation with respect to the data distribution, right? So you go through every x that can possibly happen, you weight it with the data density, and then you look at the difference between the derivatives of the log data distribution and the log model distribution at every point. So you kind of like have these two curves, you look at the slopes at every point and you compare them. And you can expand the square. It's a square of a difference, and so if you expand it, you're going to get three terms. You're going to get a blue term, which is just the square of this first gradient of the log data density squared. Then you have the gradient of the log model density squared. And then you have this red term where you have basically the dot product between the cross product between model and data. And you can kind of see that the first term does not depend on theta, so we can ignore it for the purposes of optimization with respect to theta. We can ignore the blue term. The green term is easy, it just depends on the model. So again, we're good. The problem is the red term, because that one still involves this log gradient of the log data density in some non-trivial way. And what we're going to do is we're going to use integration by parts, which is usually, you remember from basic calculus, it's a way to write the integral of the f prime g in terms of the integral of g prime f. Basically, you can which function you're taking derivative with respect to. And we apply that to that red term, which is the annoying term. Recall that this is an expectation with respect to the data of the gradient, the log data density, gradient of the log model density. Now, what is the gradient of the log of p data? Gradient of log is the argument of the log, 1 over the argument times the derivative of the argument of the log. So it should look like this. Just by expanding out this gradient of log p data is 1 over p data times the derivative of p data. And the reason we're doing it is that now this p data here and this p data here will cancel. And now it looks like kind of like something where we can apply integration by parts. So this is the derivative of p data times the derivative of the log p model. And we can apply integration by parts and rewrite it in terms of p data. So here we had a derivative of p data, and so we rewrite it in terms of just the kind of like instead of f prime, we go to f. So p data prime, it becomes p data. And then we take an extra derivative on the log, on the score of the model. And so we've basically rewritten it in terms of an expectation with respect to the data distribution of a second derivative of the model score, essentially. Now, we still have to deal with this term here, fg, which is kind of like the integrand evaluated at the two extremes. And under some reasonable assumption, you can assume that this, in the limit, as x goes to plus and minus infinity, this p data goes to 0. It's a density, so there cannot be too much probability mass at the boundaries. And if you're willing to make that assumption, this simplifies into something that now basically no longer depends on the score of the data density. It only depends on things we can manage. It's still an expectation with respect to the data density, but it only involves it no longer involves the score. And so that's basically the trick. If you are willing to assume that this term here is 0, basically that the data distribution decays sufficiently fast, then you can use integration by parts, and you can rewrite this thing, the original score matching loss. Recall it had 3 pieces. If we apply that trick to rewrite the red term into this brown term that we just derived using integration by parts, now we get a loss function that we can actually evaluate and we can optimize as a function of theta. We have the first term, which is constant with respect to theta, so we can ignore it. We have an expectation with respect to p data of the derivative squared, and then we have an expectation with respect to p data of the second derivative of the log likelihood. And so this is basically what you can write the two expectations as a single expectation, and now we basically derived a loss function that is equivalent up to a constant to where we started from, but now it only involves things we have access to. It only involves the model score and the further derivative of the model score. Just the second derivative of the log likelihood. But again, derivatives are always with respect to x. And so that's where kind of like the magic happens. This is how you get rid of that dependence on the score of the data density and write it down using elementary calculus into an expression that is now something we can actually optimize. We can evaluate and optimize as a function of theta. So that's sort of like at least in the 1D case. And it turns out that there is something, you might have seen it in multivariate calculus. There is an equivalent of integration by parts. There's actually Gauss' theorem, where you can basically do the same trick when you have a vector. So when x is a vector and you really have gradients, you can basically use the same kind of trick, and you derive something very similar, where instead of looking at the square of the derivative, you have the L2 norm of the gradient. And instead of having just the second derivative of the log likelihood, you have the trace of the Hessian of the log probability. So again, you have to look at second order derivatives, but things become a little bit more complicated when you have the vector valued kind of function. And so the Hessian is basically this matrix, n by n, if you have n variables, where you have all the mixed second derivatives. Partial derivatives of the log p theta x with respect to xi, xj for all pairs of variables that you have access to. So again, kind of like a Taylor expansion up to second order, if you want.
Is that trace operator?
And that's the trace operator. Yeah.
Oh, so just take all the
elements in the diagonal. Yeah. So it's all the kind of second derivatives.
So it's also return and a vector.
The trace will return a scalar. You sum them. Yeah. And so that's how you basically using the same derivation, but using integration by parts, you again write it down in terms of a quantity that no longer depends on the score of p data. And that's an objective function that we can now optimize. If you're willing to approximate this expectation with a sample average, we always have access to samples from p data, so we can approximate that expectation using samples. Then you get an algorithm or a loss that looks like this. You have a samples of data points that you sample from p data, training data. And then you can estimate the score matching loss with the sample mean, which would look like this. So you go through individual data points, you evaluate the gradient of the energy at each data point, you look at the square, at the norm of that vector, and then you need to look at the trace of the Hessian of the log likelihood, which is this, again, sort of like Hessian of f theta in this case, which is the model. And then this is now a function of theta that you can try to optimize and minimize with respect to theta. You recall, we're trying to minimize this is equivalent up to a shift independent from theta. It's equivalent to the Fisher divergence. And so if you're able to make this as small as possible with respect to theta, you're trying to match the scores of the data distribution and the model distribution.
Getting the Hessian of some model is like, or even the trace of the Hessian for that matter, is not very trivial, is it?
It's not trivial. Yeah, that's a good point, and I think it's going to come up soon. It still has issues with respect to very high dimensional settings, like the trace of the Hessian. I know it requires higher order differentiation, and it's somewhat expensive, but there's going to be ways to approximate it. The key takeaway is that it does not require you to sample from the energy-based model. This is the kind of loss where you just need to training data, you evaluate your neural network, and you don't need to sample from the energy-based model during a training loop, which is key if you want to get something efficient. And the loss function actually have this is kind of like what you just brought up, that indeed the Hessian is tricky, but it has a reasonable flavor. Like if you think about it, what is this loss saying? You try to minimize this quantity as a function of theta. So what you're saying is that you should look at your data points and you should look at the gradient of the log likelihood evaluated at every data point, and you're trying to make that small, which basically means that you're trying to make the data points kind of stationary points for the log likelihood. So the data points should either be local maxima or local minima for the log likelihood, because the gradients at the data points should be small. So you should not be able to somehow perturb the data points by a little bit and increase the likelihood by a lot, because the gradients should be very small evaluated at the data. That's kind of like what this piece is doing. And this piece is kind of like saying, trying to make sure that the data points are local maxima instead of local minima of the log likelihood. And to do that, you need to look at the second order derivative, and that's what that term is doing, which is kind of very reasonable. It's saying, if you want to fit a model, try to choose parameters so that the data points are local maxima somehow of the log likelihood. And that can be evaluated just by looking at first order gradients and second order gradients. Yeah.
So using the trace of the Hessian, could we figure out this local minimum maximum just by like looking at points around it and seeing if they're higher or lower?
Essentially, yeah. So that's essentially what we're going to do. Is we're going to there's two ways of doing it. One is to, I guess, something called slice score matching, where you're kind of taking random directions and you're checking whether the likelihood goes up or down along those directions, which is the same as if you know about the Hutchinson trick for estimating the Hessian. It's basically the same thing, where it's an estimator for the trace of a matrix that kind of looks at that kind of like at a random projection around, at a random direction around it. And the other thing is denoising score matching, which also has this flavor of sort of like adding a little bit of noise and checking whether the likelihood goes up or down in the neighborhood of a data point. And so it has that flavor, basically. And those things are going to be scalable with respect to the dimension. Yeah.
Does Hessian have a fixed analytical form? when you're taking derivatives with respect to x?
So it doesn't in general. So the question is, has the hash an analytical form? Like if theta is a neural network, you can't, there is no close, I mean, you have to use autodiff to basically compute it. The problem is that it needs many backward passes, kind of like there isn't, because you're not computing just a single partial derivative, you're computing n partial derivatives with respect to every input, because kind of like you have to compute all the diagonal elements of the Hessian. And we don't know of an efficient way of doing it other than doing backprop basically n times, which is also expensive when n is large. But the good thing is this avoids sampling, and this is going to be kind of like the key building block also for training diffusion models. But more of this in the next lecture. Oh yeah, question.
Would converge to, would want a sharper point peak rather than, so there might be a really sharp thing that's like pretty low and then a smoother higher.
So it doesn't happen in the sense that I just proved you that this is equivalent to the Fisher divergence, and the Fisher divergence is 0 if and only if sort of like the distributions match. So even though, yeah, you might think that this is not quite doing the right, it's not quite the right objective, in the limit of infinite data, this would be giving you exactly the, if you were to optimize it globally, this would give you exactly the data distribution. Because it's really just equivalent up to a shift to the true Fisher divergence that we started with, which is this, this thing here, which is 0 only basically if the densities match. Cool. Now the other cool technique that you can use for training, yeah, so that's sort of like the takeaway so far is that KL divergence, approximations to KL divergence or MLE require sampling, too expensive. But you can, if you are willing to instead measure similarity up here using this Fisher divergence, then again you get a loss function that is much more, that is very suitable for training energy-based models because it does not require you to, even though it looks tricky to compute and optimize, it actually can be rewritten in terms of something that only depends on the model and you can optimize as a function of data. Now there is another way of training energy-based models, which is going to be somewhat loosely similar to generative adversarial networks, which is essentially a way to fit an energy-based model by, instead of contrasting data to samples from the model, we're going to contrast the data to samples from some noise distribution, which is not necessarily the model distribution itself. So that's how it works. You have the data distribution, and then there's going to be a noise distribution, which is any distribution you can sample from, and for which you can evaluate probabilities. And what we're going to do is we're essentially going to go back to the GAN idea of training a discriminator to distinguish between kind of like data samples and noise samples. So far, there is no energy-based models, just the usual kind of GAN-like objective. And the reason I'm bringing this up is that if you had the optimal discriminator, then you would somehow get these density ratios between the noise distribution and the data distribution. So recall that if you train a discriminator optimally by minimizing cross entropy, and so if you're trying to discriminate between real data and samples from the noise distribution, what is the optimal discriminator? It has to basically give you the density ratio. For every x, it has to be able to know how likely x is under data and how likely x is under the noise distribution. So useful recap for the midterm. It's this is the optimal discriminator. It's the density ratio between. So for every x, you need to figure out how likely it is under the data versus how likely it is under the data and the alternative kind of noise distribution. And the reason I'm bringing this up, because what we could try to do is we could try to basically parameterize the discriminator in terms of our generative model, which could be an energy-based model. So we know that the optimal discriminator has this form, p data over p data plus noise distribution. And so we could try to just define a discriminator. So instead of having your whatever MLP, whatever neural network you want to discriminate between data versus noise, we're going to define a special type of discriminator where when we evaluate the probability of x being real data, we get that number instead of like just feeding x through a neural network arbitrarily. We get it by evaluating the likelihood of x under a model p theta versus the probability under the noise distribution, which again we're assuming is known because we're generating the noise distribution, the noise data points ourselves. And so the good thing is that if you could somehow come up with the optimal discriminator that distinguishes data versus noise, we know that the optimal discriminator will have this form, and this has to match the p data over p data plus noise. And so you can see that somehow, if this classifier is doing very well at distinguishing data from noise, it has to learn, basically p theta has to match p data. So the classifier is forced to make decisions based on the likelihood of x under p theta. And then if it's able to make good decisions, then this p theta has to match the data distribution, basically. That's essentially the trick that we're leveraging here. And then what we're going to do is we're going to actually parameterize the p theta using an energy-based model. But that's kind of like the key idea. Instead of using an arbitrary neural network as the discriminator, as you would do in a GAN, we're defining a discriminator in terms of another generative model. And the idea is that by training the discriminator the usual way, by minimizing cross-entropy loss, we're kind of forcing it to learn a p theta that matches the data distribution. Because that's the only way it can do well at this binary classification task. It really needs to know which x's are likely under p data to get good cross-entropy loss. And that's only possible when p theta matches p data. And we're going to see that this is suitable when p theta is defined up to a constant, kind of when p theta is going to be an energy-based model. So, well, yeah, maybe let me skip this since we're running out of time, but you could also use the classifier to correct the noise distribution. But for now, let's assume that p theta is an energy-based model. So we're going to parameterize p theta in that previous expression in terms of an energy, usual trick, just define up to a constant. And what we're going to further do is, in general, this normalization constant, z theta, is a function of the parameters f theta, and it's a complicated function because we don't know how to compute that integral, that sum over all possible things that can happen. And so what we're going to do is we're going to treat z theta as being an additional trainable parameter. So not only we're going to optimize f theta, but we're going to treat z theta itself as an additional trainable parameter, which is not explicitly constrained to take the value of the normalization constant. It's going to be some other scalar parameter that we can optimize over. And so if you do that, then basically the density model that we're going to use in the classifier now depends on theta and depends on z. And then we just plug this, the idea is that basically if we plug in this expression into the classifier, into the discriminator, and we train the discriminator the usual way by minimizing cross-entropy, we know that under the optimal parameters, this classifier will have the density model that we're using to build the classifier will have to match the data distribution. And what this means is that the optimal theta and the optimal z are going to be such that the energy-based model is equal to the data distribution. But crucially now, z is just a learnable parameter. It happens to be the correct partition function in the limit, because you take the integral of both sides with respect to x, you're going to see that the integral of this optimal energy-based model is equal to the integral of the data, which is 1 by definition. So even though we treat z as a learnable parameter, in the limit of learning an optimal classifier, this learnable parameter that is not constrained to be the actual partition function will take the value of the true partition function of the model. Because that's what sort of like the optimal classifier should do if it does really well at this binary cross-entropy classification loss.
In this case, like
it's not easy to converge, actually. So the loss function ends up being, let's see, something like this. So if you plug it in, recall, we're basically saying we're going to, instead of picking an arbitrary neural network for the discriminator, like in a GAN, we're going to pick a neural network that has a very specific kind of functional form, so that when you evaluate what is the probability that x is real, you have to get it through this kind of computation. But you have an energy-based model that tells you how likely x is under the model, where both f theta and z are learnable parameters. And then, if you just multiply numerator and denominator by z, you get an expression that, again, as it should, depends on f theta and z, and the noise distribution, which is known. Pn, the noise distribution, is again something that we are deciding. You can pick whatever you want as long as you can sample from it and you can evaluate probabilities under the noise distribution. And then literally what we do is we still train the classifier by doing binary classification with cross-entropy loss. So we have, just like in a GAN, we have data, we have real data, we have fake data, which is generated by this noise distribution, which we decide ourselves. So this is different from a GAN. The fake data is coming from a fixed noise distribution. So we're contrasting the real data to fake samples generated by the noise distribution. And we're training the classifier to distinguish between these two. And the classifier has this very specific functional form where it's defined in terms of an energy-based model, where the partition function is itself a learnable parameter. And then we optimize this with respect to both theta and z, trying to do as well as we can at this classification task. Yeah?
With this scheme, how will the samples you end up generating in the end be good? Like, it doesn't seem like it would be very hard to discriminate between even like a crappy generated sample and noise.
Yeah, so what happens is that in theory, this works regardless of what is the noise distribution. In practice, what you want is you want a noise distribution that is very close, kind of like to the data distribution, so that the classifier is really forced to learn what makes for a good sample, what makes for the real, what kind of structures do the real samples have. At the end of the day, what you learn is you learn an energy-based model. So you learn an f theta and you learn a partition function. And in the limit of infinite data, perfect optimization, if you optimize this loss perfectly, the energy-based model matches the data distribution. And the partition function, which is just the value of this learnable parameter z that you get, actually is the true partition function of the energy-based model. So even though we're just training it in an unconstrained way, so there is no relationship here between theta and z, it just so happens that the best thing to do is to actually properly normalize the model, where z theta becomes the partition function of the energy-based model. So in principle, this does the right thing. In practice, it heavily depends on how good the noise distribution is.
We're not really explicitly training a discriminator. We're just adding a new trainable parameter to our generator.
So we are training an actual, so there is no generator. The generator is fixed, or you can think of it as being fixed. So the noise distribution, it would be the generator, and that's fixed. we are training a discriminator, but it's a very special discriminator. So you're not allowed to take X and then feed it through a ConvNet or an MLP and then map it to a probability of being real versus fake. You have to get the probability by using this expression.
Yeah, it's just like once we finish the F theta is just for generative. That's how
yes, yeah. In that sense, yes. There's only a discriminator. Once you've trained it, you can extract an energy-based model, which is the F theta, from the discriminator.
Use a fixed noise distribution or sample without noise distribution.
Yeah. So in this flavor, which is the simpler version, the noise distribution is fixed. We'll see soon, if we have time, in a couple of slides, that indeed it makes sense to change the noise distribution and kind of like trying to adapt it and make it as close as possible, kind of like to the data or the current best guess of the model distribution. And so, yeah, that's an improvement over this basic version of things where the noise distribution is fixed for now.
How would you sample in this procedure?
So we're assuming that the noise distribution is something you can sample from efficiently. So you can always basically get, do some kind of stochastic gradient ascent here on this. Once you've trained the model, so the learning is fine. It's efficient as long as Pn is efficient to sample from. You never have to sample from P theta. Once you've trained the model, you have an EBM. And so if you want to generate samples from it, you have to go through the MCMC, Langevin. So at inference time, you don't get any benefit. This is just a training time. This loss function does not involve sampling from the model.
Can we sort of allow Z not to be the integral? Why is that fair game?
It's fair game in the sense that only to the extent that in the limit, you will learn a partition function. In general, you will not. And so the solution to this optimization problem will give you a Z in practice that is not the true partition function of the model. It's just going to be an estimate. And you're going to end up with an energy-based model that is suboptimal because you're sort of, the Z that you estimated is not the true partition function for that model. And so when you have finite data, imperfect optimization, you pay a price for this approximation. But in the limit of things being perfect, this is not an issue, basically.
So if you have infinite data like Z, you will probably converge to the integral.
Yeah, so if you have infinite data and somehow you're able to perfectly optimize over theta and Z, then we know that the optimal solution over theta and Z will be one where this matches the data distribution. And so the only way for that to happen is for Z star to be the true partition function of that energy-based model. But in practice, this is not going to happen. So you just get an estimate. Yeah.
So if it's not the true partition function, you won't have like a valid probability distribution, right, for P data? Is that fine?
So yeah, so that's a great question. So if it's not a true partition function, you still have an energy-based model for which there is going to be a real partition function. It's just not the one you've estimated. So F theta still defines a valid energy-based model. It's just that the partition function for that model is not going to be the solution to this optimization problem over Z. So it's not going to satisfy the constraint. But there's going to be a partition function for that F theta, so that's going to be a valid energy-based model.
Implementationally, this seems like because you're sort of letting go of the constraints on and all these sorts of things. So like implementationally, this must be like a harder optimization problem compared to something like a score-based model, or implementationally is this like somehow it works?
Yeah. So this is the implementation. It's actually not too. We'll see soon, and then you can ask again if it's how it's implemented. It's not it's a relatively simple kind of like loss to optimize and write down. It's actually trivial to implement.
You are sort of almost guaranteed that you're going to get a suboptimal, like F theta x, right? And because your Z theta is different approximation. So like my question is that if I train sort of this and a score-based model, am I guaranteed that the score-based model for the extra effort I put in there is going to be like sort of a better model?
So it turns out that they're actually very much related, and if the noise distribution is kind of like what you get by perturbing data by adding a little bit of Gaussian noise, essentially, then this turns out to be exactly denoising score matching. So it very much depends on the noise distribution that you choose. But there are instances where this becomes exactly score matching. So I don't think it's fair to say that this is always bad. It's just a different thing. Yeah.
Yeah, going back a bit, is the partition function something you can normally compute for energy-based models, or?
No, you cannot.
You can.
Yeah, that's the problem. Yeah.
Then, so generally, the training methods don't involve a use like these different methods.
Yeah. So either you do contrastive divergence, where you would sample from it, and so in some sense it involves the partition function in the sense that you would estimate the gradient of the log partition function by using samples from the model, but that's also too expensive. Or that's exactly what we're doing right now. Let's come up with a training objective that does not depend on the partition function. So it's going to be efficient. Cool. And then, yeah, so then for numerical stability, let me see, what do I have here? So yeah, that's the objective. And then you plug in the expression for the discriminator in here, and you get a loss that looks like this. And you have the log of sum of two things. And so for numerical stability, it's actually easier to use the log sum exp kind of trick, where the log of E of f theta plus ZPN, which is kind of like what you have in the denominator, it's more numerically stable to write it as a log sum exp. But then practically speaking, the implementation is very simple. You start with a sample, a batch of data points. You have a batch of noise samples, and you just do, basically, you have this classifier, which has a very specific functional form, and just you evaluate the cross-entropy loss of that classifier on this mini batch, which happens to have this kind of functional form. And then you optimize it as a function of theta and z. And that's just basically what we had before. And so you're kind of like evaluating the loss of the classifier over these two batches of real and fake, or real and samples from the noise distribution. And then you try to maximize this as a function of theta and z. And yeah, stochastic gradient ascent with respect to theta and z. And again, key thing, you don't need to sample from the model. And you can kind of see that the dependence on z is non-trivial in the sense that sometimes it's not optimal to just make z as small as possible or as big as possible. It depends on z in some non-trivial way. And so there is some interesting learning happening here over both theta and z. But at the end of the day, yeah, you end up with an estimate of the energy of the model, f theta, and an estimate of the log partition function. And everything can be trained without using samples from the energy-based model. So it looks a lot like a GAN, generative adversarial network, in the sense that in both cases, you are training a discriminator with binary cross-entropy. So that part is the same. Both are likelihood-free. We don't have likelihoods in EBM, so it better be. There is never a need to evaluate likelihoods under the EBM or under the data distribution, because we don't have either of them. So it's all just like a standard cross-entropy loss, basically, on a classification task. So reduced to a discriminative modeling, kind of generative model to discriminative classifier kind of training. The key difference is that in a GAN, you are actually have a minimax optimization where you're also training the noise, so you're training the generator. Here we're not. So here, this is stable, it's easy to train. The noise distribution is fixed, and you're just maximizing that objective function as a function of theta. It's non-convex, but there is no minimax, there is no instability. It's actually relatively stable to train. The kind of slight difference is that in noise contrastive estimation, you need to be able to evaluate the likelihoods of the contrastive samples that you generate from the noise distribution, while in a GAN, you just need to be able to sample from the generator. So if you look at the loss here, we need to be able to evaluate when we generate from PN, from the noise distribution, we also need to be able to evaluate how likely these noisy samples are. In a GAN, you don't have to, you just need to be able to generate them fast. So that's slightly different. And when you train the NCE model, you kind of just train the discriminator, and then from the discriminator you get an energy function which defines an energy-based model, while in a GAN you're actually training a deterministic sample generator. So the outcome of the learning is going to be different. And maybe the last thing that I'll say is that kind of like what was suggested before is that it might make sense to adapt the noise distribution to the as you go during training. And so instead of keeping a fixed noise distribution, we can try to learn it jointly with the discriminator. So recall, we need a noise distribution that we can sample from efficiently, and we can evaluate probabilities over efficiently. And so the natural candidate is a flow-based model for this. And intuitively, we're kind of like training the noise distribution to make the classification problem as hard as possible, so that the noise distribution is close to p data. And so the flow contrastive estimation is to basically this idea where the noise distribution is defined by a normalizing flow with parameters phi. And then it's basically the same, except that now the discriminator depends on the noise distribution, which is a flow model. So it will depend on the parameters of the flow. A flow model, you can sample from efficiently, you can evaluate likelihoods efficiently, so it fits with this kind of API. And then now we optimize the discriminator over theta and z the usual way by noise contrastive estimation. And then what they proposed is to train the flow model to kind of like in a minimax way, so it goes back to GANs in some way, by kind of like train the flow model to confuse the discriminator as much as possible. And so that's kind of like their proposal.
I'm curious, in the end, does the flow model perform better, or does the EPM perform better?
In the end, they use the flow model. So here are some samples, and then they are actually generated from the flow model. Although technically they get both. They get an energy-based model and they get a flow model, and they show that for some things, you're better off using the energy-based model. But yeah, you get both at the end of the day. It's more like a GAN. Yeah, so basically noise contrastive estimation, where the noise distribution is a flow that is learned adversarially. Recall that the inside, this max here inside, is basically the loss of a discriminator in a GAN. It tells you how confused the discriminator is. And so, well, not how confused, how not confused. And so by minimizing it, you're trying to make the life of the discriminator as hard as possible. And so you're learning something by minimizing a two-sample test, essentially. And so it's the same as the usual GAN training. And then, yeah, here are some samples that they generated in the model. And I think this is probably a good time to stop. I think we're out of time.